8.8 is on improper integrals. So suppose you had a function that looks something like this. So let's draw this. And let's see, you go from, say, a, and this would be like a t value or something. It doesn't really matter. Well, we're going to call that x. And you say you have a function that goes like this, but it doesn't, it approaches infinity. So how do you integrate that? Like, how do you do an integral that gives you that entire area? And so you want all this area, but then it keeps going, it doesn't stop. So I'll fill that in. So you have all this, but then it tapers off little by little, but you want to include that. You don't want to stop wherever you're at. So this is what we have. I'll call that F. So suppose F is continuous on 0, or not 0, sorry, starting at A. At A, and then to infinity. So in other words, A is greater than 0. And we have that the limit of f of x as x approaches infinity equals 0. So it can't like take off to infinity, otherwise the area will be infinite. So if t is greater than a, then, oops, I wrote an a there, then we have what we define as a of x is equal to the limit as t approaches infinity, the integral from a to t of f of x dt. If the limit exists, so if the limit exists, the limit is the area from a to infinity, or technically it's approaching infinity, but we just say that kind of loosely. So, and so what you have then is it's like you stop at t, but then you say, oh no, let t approach infinity. So the notation you actually use will look like this. So here's a definition. So this is what you write given something that's like this. They'll put infinity up here or down here. I'll show you the 3 different cases, but you have to convert it to this form. So if f is continuous on R, and it doesn't actually have to be continuous on R, but I'm just saying it's continuous where we're talking about. That way it'll be integrable. So then the integral of a to infinity of f of x dx. So if you're given that form, then you need to convert it to the limit as t approaches infinity, and you put in this dummy variable t and then evaluate. This is what you end up doing. And then you just have the other cases. You have the other case that goes from negative infinity we'll say to b of f of x dx, and then that's the limit as t approaches negative infinity, integral from t to b. So that would be going basically, just flip this whole thing around and going the other direction. Then it's f of x dx. And so you evaluate, substitute in your values for b, and then the variable t, and then you let t approach either negative infinity or positive infinity. The other case is if you both are approaching infinity. So if you write negative infinity to infinity, what that means. So this is the improper case. That's what we mean by improper. So what that means basically is you have to break it up. You go from negative infinity to something in the middle, k, and you pick just a convenient value, and then k to infinity, and then you apply the same stuff above, of course. And k can be anything in the reals. But, like if you have a function and it does that, and you pick like 0 and do one side at a time. Okay, so let's look at this example. So evaluate the integral from 2 to infinity of 1 over x minus 1 squared dx. And so our function f of x is 1 over x minus 1 quantities squared. So that is just the 1 over x function that's shifted. So you want to graph that and see what it looks like. So graph whatever that is. You want to always graph, if you can, pretty much everything on this that I have you do, because you want to get a feel for it. I don't see enough graphs in your work. So this is 1 over x squared. So you shifted 2 units, and then you have the vertical asymptote. Why didn't that do that? The vertical asymptote at 1. Did I say 2 units? I'm sorry. It shifted 1 unit over. I just didn't. So we'll call that 1. So this is the line x. Oops, switch back. This is the line x equal to 1. And our graph will look like this. It's on both sides. It's symmetric with respect to the x equals 1. Okay, I'm going to have to turn this. You can't see me turning it, but I'm turning it so I can draw a better graph. That's pretty close, and it's asymptotic right there, of course, and down here. And so this integral is going from 2, actually, that's right. Let me fix this. I know this is tedious, but I can't help it. All right, so we're going to go, I'm going to bring this in so the graph looks better. Sometimes I like to do it in gray because it's kind of just a dotted. I think you can see that all right. Okay, so that's my vertical asymptote, like that. And we will go ahead and do this in green. And I'm going to make it a little bigger so you can see what it does. So it goes like this, like this. And so you want to, we're going from 2, and we want to find that area here. So we want to look for all of this area from 2 and then approach infinity. So what does that area get close to as you keep going, basically? So that's the idea. So as you keep adding area way down here, as you keep adding it up, it's going to approach what number? Okay, and we say it equals that number when you approach infinity or get to infinity, if that makes any sense. So you need to write this as, and a lot of this section is proper notation. You have to have the proper notation. Sometimes you'll get the right answer, especially in the next thing I'll show you. But for infinity like this, you can't just like plug in infinity. That is a no-no. You cannot just substitute infinity in. You have to take limits. That is mathematical faux pas, to plug in infinity. Okay, so now we're doing the limit of all that of x minus 1/2 dx as you approach, as t approaches infinity. So now I put in my dummy variable, the t, and when I evaluate, I'll put in t and then take the limit. So this is equal to the limit as t approaches infinity, and then you get -1 over. So you just integrate, right? So you bring that up, you add 1 and divide. It's negative, so you get just a -1, and then oops, and then it's x minus 1. So x minus 1, and then you evaluate that from 2 to t. So it's critical here to bring down everything, including the limit. This notation, remember, you're communicating your work. You're not just doing the problem. So if you drop it, it's illogical. The logic stops. So make sure you bring down your limit. And then it's -1 over t minus 1 minus -1 over 2 minus 1, which is equal to the limit as t approaches infinity. And then it's -1 over t minus 1, and then that's just +1. Now, take a limit. When you take a limit as t approaches infinity, this is fixed on top. This t value here is approaching infinity, a fixed value over something giantly large. That approaches 0. So that whole thing is approaching 0 as t approaches infinity. Therefore, this equals 1. So the area under that curve is 1. Okay, so that's what you get. And you can actually say that. I mean, as you approach infinity, the actual mathematics is a summation, and you're getting it closer and closer to 1 the more area you add up. It is not diverging. But we can say, we can actually say that the area under that curve is exactly 1, which is kind of cool. So some of the wording we would say is something like this. We'd say, thus, given our conclusion there, the integral converges, because it's a summation, it's an infinite sum, right? So the integral converges and has the value 1. But we literally can say the area under the curve is equal to 1. Like if it kept on going, but it is. Okay, let's see what we got here. Okay, let's do one more, because then I got about 3 of them. So we'll do another one, and then we'll do another video. Okay, next example. What is this one? Yes, I like this one. Okay, so integral from 2 to infinity, and again, I use that term loosely, x minus 1 dx. All right, so the first thing you want to do, write that with your t variable. So replace infinity with your t and do your limit as t approaches infinity. You must do that. So limit, you don't have to use t, but you must use something other than x. The limit as t approaches infinity, integral 2 to t of 1 over x minus 1 dx. So do we recognize this integral? What is that? Yes, that is natural log. So you have a natural log on that one. So you have the limit as t approaches infinity of, and so that will be ln x absolute value of x minus 1 from 2 to t, and it's positive, so we don't have to worry about the absolute values. So that equals the limit as t approaches infinity, and then so that'll be ln absolute value of t minus 1, and you could drop it there because t is getting large, positive, minus ln, and then that's just 2 minus 1. Okay, keep on going. So that's the limits as t approaches infinity of so that'll be ln absolute value of t minus 1. Oops. Rewrite that. So natural log of 1. What's natural log of 1? So this here, oops, I don't like that color. This here actually equals 0 because ln 1 is equal to 0, right? It goes like this, it goes through 0 at 1. It's not approaching, it's actually equal to 0. And so now you get the limit, so you just have the limit of the natural log of t minus 1, and you don't need absolute values, you can put them if you want. But that's a natural log function approaching infinity. So this equals infinity. So this integral basically shows that it diverges. So this is something we'll see again later. I'm going to draw this picture here. So you have, we're at 1 is the shift, and then my graph does this, right, just like the other one, but it's a different, it doesn't approach as quickly because it's not being squared. And then it's down here as well, like that. And so you're still looking at this area from 2 approaching infinity like that. And we're coming up, this we were doing, starting at 2. And so this case, you have infinite area. This case, you have finite area. The area converges to 1. This case, it diverges. So therefore, diverges. So that's kind of a critical difference. And we will talk about that more on sequences and series in the next chapter. So this divergence, because this is just 1 over, it's like 1 over x essentially, and you get infinite area. So v equals infinity, so you can say therefore the integral diverges is the terminology we use. Okay. Now we will do a case where we're going to look at what happens if you want to go like this and approach 1. So what do you do with that? You're going to approach basically on the right or left and take a limit. Same concept, but so we will look at that next.